All right, 2.1, applying now the idea of the limit to the first half of the calculus for differential calculus, it's called, for the house of calculus that we're going to be building. So this is a tangent line problem, and this was one of the motivating factors for discovering the calculus. There were several impetuses, if you will. The tangent line problem was kind of the Leibnizian motivation. So Leibniz, of course, bless you, is one of the founders of calculus. He discovered it in Germany in the 17th century. His poster is by my desk. He probably is not somebody you've heard of unless you are into the philosophy of binary numbers. There's an argument that could be made that he, not Charles Babbage, is the father of computer science. He built an entire religion based upon the numbers 0 and 1, where 1 represented the eternal and 0 represented the void, okay, heaven and hell, if you will. So an interesting guy. But he discovered calculus roughly the same time as Isaac Newton, who you've probably heard of, right? Especially if you've eaten his wonderful, delicious fig cookies. Roughly the same time in a different part of the world, motivated by a completely different thing and using completely different notation, okay? But they became a priority dispute because Leibniz apparently discovered it first, or Newton supposedly discovered it first, but didn't publish his work. And then Leibniz did publish his, and then it circulated throughout Europe. And then Newton said, hey, I've done this already, and said, you stole it from me. He accused him of stealing the calculus, which was really unlikely because completely different, as I said, notation and motivation. But Newton went on then to never not publish his stuff ever again, and he eventually became head of the Royal Society. Those are the guys that wear the big white wigs, and they were kind of the custodians of the intellectual property of the day. And so when you're in charge and you want calculus on your resume, what do you do to the other guy who's challenging your right to sole authorship? You make sure he's a footnote in history, right? So Leibniz was kind of discredited in his day. He did have some supporters, though, the Bernoulli Brothers, if you've ever heard of them. They're not a comedy team, but they were astounding brothers intellectually, and they made great contributions themselves to calculus, but they were big proponents of Leibniz. But, of course, Newton kind of won. He won everything that he did, Newton, except alchemy. He was never able to spin straw into gold or whatever. Yeah. Anyway, the harbingers of chemistry, the alchemists. So anyway, the tangent line problem was Leibniz's perspective. The motion of the planets was Newton's perspective, and we'll look at that later on. So let's look at the tangent line problem. First of all, what is a tangent line? You remember from geometry? It's a line. Okay, Slater's saying it's a line, I guess. It could be vertical. Yeah, 1 point. So in geometry, you had circles, and then maybe you had the vocabulary word that this line comes off and kisses the graph at 1 point. And here's the radii, and you have this property that tangent lines are at right angles to the radial lines in a circle. Okay, so that's what a tangent line is. A tangent line basically glances off a function in one point. Okay, so if you have a function that looks like this, f of x, would this be a tangent line right here if it intersects at once? No, that's not a tangent line. It has to be something that glances off there. So think about like surfing the curve, right, dude? Surfing the curve, dude. This would be the tangent line, okay? And as you move it from left to right, it's going to change, right? So it turns out that finding the slope of that tangent line for a function became exactly the same answer to how fast are the planets moving in their orbits, okay? And they both are centered around the idea of the derivative. Leibniz called his derivative the method of infinitesimals. So what does infinitesimal mean? Infinitely small. And Newton called his the method of fluxions, the root there being flux, which means to fluctuate or change, right? So he was motivated by motion. All right, so let's see then why the tangent line was such a problem. We might get cut off before lunch. So to explore the idea, you can not see this parabola as you zoom in, but the graph of f of x equals 3x minus x squared is shown above. So 3x minus x squared, you can quickly If you wanted to set it equal to 0, factor out an x, and you get 3 minus x. So you can tell what the x-intercepts are very quickly. So there's one right here at 0, and then there's one over here at 3. And parabolas have symmetry through their vertex. So if you want to know the x-coordinate of the vertex, all you have to do is average the x-intercepts. So what would that be? 1.5, yeah. So that one's marked right here. So 1.5 is the x-coordinate of the vertex. Okay, sweet. I wish it showed it better, but y'all have it in front of you. Here's what we want to know. How fast is the graph of f of x? That is, how fast are the y values? When we say how fast is f of x, we're talking about how fast are the y values changing with respect to x at x equals 1. Okay? So here's x equals 1 right there. So if I go straight up, it's going to be right around here, I think. Let me see. It's going to be at 2, so maybe I go up a little higher. Come straight across, right around there. Okay, so this is the ordered pair 1, 2. First of all, what does it mean for me to ask how fast is that graph changing at that point, or how fast are the y values changing at that point? It's the slope, right? Essentially, in Algebra 1, you learned that slope was not just rise over run, but it was the rate of change of the graph. It's the average rate of change in Algebra 1. And in Algebra 1, we have a line, right? And lines have the constant slope everywhere, so their rate of change anywhere at any point is the same as their average rate of change between the 2 points. They have a constant rate of change, or a constant slope. So we have a parabola here that does not have a constant slope. The y values are increasing and then decreasing, and they do so at variable rates. Yeah? It's steeper at the bottom, so as we start coming up, the y values are increasing rapidly, but then as we approach the vertex, they're still going up, but not as quickly, and then, of course, they go down slowly and then a little bit faster. So we're looking at essentially the speed of how fast the y values are going up with respect to moving to the right. So yes, if I want to know how fast this graph is changing, or the y values at this point, it's essentially trying to find the slope of that tangent line. If I could figure out the slope of that tangent line, I can figure out how fast that graph is changing. So what is the problem then? Lines are easy to use, but to find the slope of a line, you need how many points? I need 2 points. Well, I have the point 1, 2. Do I have another point on the line? I don't, okay? I can guess, but then what good is the guess? It's not accurate, right? So there is the problem. The problem is, how do you find the slope of a line when the algebra of the day requires 2 points, change in y over change in x, and you only have 1 point? Well, if you're Newton or Leibniz, you invent a new branch of mathematics called calculus, okay? So every genius can always cleverly circumvent the limitations of the day. So when you get back from lunch, we'll take a peek at how they went about doing that. Have a great lunch.